SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We discussed about the surface operated process like the residual concentration, and tried to just get an overview, basic idea as to how this process operates on the surface and the necessary conditions, the topographic and the climatic conditions that is needed for getting these materials enriched to the ore grade for aluminum, nickel, gold, or for that matter even iron ore. So, we will discuss another such important enrichment process where actually it is essentially a process by which a primary ore gets enriched or gets concentrated in a definite part of it by the process of interaction with interaction of meteoric water with an existing ore body. So, we will look at this, we call this process essentially as a supergene oxidation and secondary sulfide enrichment process. If you look at it, this is just a cartoon that depicts the scenario here. What is shown here is, for example, say it is a tabular or a tabular ore body which extends to depths of several hundreds of meters from the surface. This deposit definitely formed at a deeper conditions in the crust when it formed primarily, and now this deposit has been exposed or is exposed to the surface, and this has been a primary ore body of a metal sulfide and has abundant pyrite FeS2 as the dominant mineralogy, along with other sulfide minerals like it could be chalcopyrite, it could be galena, sphalerite type of sulfide minerals. And suppose this particular ore body is now exposed to the surface. Look at this, if in relation to this diagram, what is shown here is as WT is the water table. We all know that water table is the surface indicates that if we dig a hole here, the level at which we will get water, that's a surface which will be essentially in an unconfined condition is the water table. So, above the water table, the condition here is actually known as the zone of aeration, where the pore spaces in the rocks or the fractures are either partly filled up with water or are filled up with air, and that is how we call it as a zone of aeration or zone of oxidation. And below the water table, this zone where the pore spaces are fully filled up with water, and this zone is a zone of reduction. The significance of this with respect to this ore body which is exposed at the surface is like this. We have the primary sulfides essentially dominantly pyrite on the surface. So, one of the necessary conditions for this process to operate is that the ore body has to have a certain abundance of the mineral pyrite. Why is it so? We will just see in a while. So, what happens here, that the primary pyrite gets oxidized in the presence of water and oxygen and generates huge amount of sulfuric acid H2SO4, and this H2SO4 which is generated here in this zone is it actually dissolves the other metals like lead or zinc or copper which are there in minerals like chalcopyrite or sphalerite or galena, and then they are soluble, they are converted to their very soluble sulfate form, and they trickle down or they they essentially they descend, because this zone is essentially is a zone where the permeability is essentially high, and through which this dissolved form of the metals like copper, zinc and lead they go down, and as and when they cross this water table and encounter a reducing environment, all these sulfates get again reduced to form their secondary sulfides. So, in terms of the process, the results are that below the water table we get some zone which we call as the secondary sulfide enrichment zone, in which the primary sulfides of the ore like chalcopyrite or galena or sphalerite are replaced or by the secondary sulfides of them. As we know that the minerals, copper minerals like chalcocite, which is chalcopyrite, which is chalcopyrite is CuFeS2 is chalcopyrite, and this is a primary sulfide of copper and iron. Minerals like Cu2S, that is chalcocite, and Cus like covellite. These two minerals which they rarely form in primary ore bodies of primary sulfide ore bodies, because the conditions that is required, the activities of the fugacity of the sulfurous species and the concentration of these ions copper, it does not allow formation of these minerals as primary minerals in the primary ore of any of the sulfide ore body that is forming the earth's crust. So, the zone which is shown here essentially are the zone in which there will be enrichment of the metal in the form of the secondary sulfides, which are the chalcocite and covellite. So, this is how the process goes on, and the what happens here is as we know that iron cannot remain in the soluble Fe2 2 plus form for long on the surface. It will immediately gets oxidized to form its respective insoluble oxide or the hydrated oxide. So, what is shown here with this orange color material is essentially this material is actually called it is like a oxide cap or oxide rich iron cap, or it is also in mining geology term it is also called as iron hat. Iron hat. This is also very popularly known by one term which is called Gosan. So, this part we can call as the supergene oxidation, and the immediately following zone just below the area is essentially the zone from which most of the metals copper, lead or zinc, depending on what the deposit is, are leached, and this is the enriched zone. And sometimes this process, if it depends if this ore body, the diameter of the ore body is such, and also it also depends on what is the immediate host rock which is there surrounding this ore body. If the immediate, because here in this zone initially there will be generation of copious amount of sulfuric acid, and that sulfuric acid means that the pH of this fluid will become very low. If the surrounding rocks which are just around the ore body, if they are able to consume the acid that is generated over here, then this process will not be able to operate that very efficiently. So, we need to have some kind of favorable host rock here, which will not be, first of all the volume of this ore body has to be adequate, substantial, so that the heat that the acid that is generated will be able to go down. And so, sometimes what happens, if if this zone the oxidation process is remains a little bit incomplete, then we do also get certain other minerals, even the metals like copper or lead or zinc, even they deposit on in situ in the form of their respective oxides, in which case the supergene enrichment zone will not be that very prominent. Supergene enrichment zone will only be prominent if we have this process operated to its full efficiency. So, now let us look at so here we can see this profile diagram again shown in a more clear way, where this zone is the alluvial zone, this is the alluvial zone, this is the leach zone, this is the oxide ore, and this is the surface left iron oxide, which is the iron hat, and this is the chalcocite covellite. Sometimes also it does contain some amount of bornite. Like this is also one mineral of copper iron, which also forms in the ore body. If you look at this situation and you take a profile of the elemental concentration, then you will get something like this. Say we are doing for copper. So, copper will be something like this and will have an increased concentration in this and goes to the normal value, because below this secondary sulphide enriched zone we get the primary ore and the copper value is decreased. If we take the iron, then iron will have a value which have a profile which will be exactly like this, which will be high on the oxidation on the zone, and this will be for iron, and this will be for copper. This will be for copper. Let us look at the mechanism, the way it works in form of the reaction. So, here we could see what exactly we discussed. The reaction is pyrite plus oxygen plus water is giving rise to ferrous sulphate, which is soluble aqueous, and generation of H2SO4. This sets up a chain reaction where the FeSO4 is again acted upon by sulfuric acid to form ferric sulphate. This ferric sulphate gets oxidized, the iron is getting oxidized to form the FeOH3, which actually is a part of that iron hat or the Gosan which we just stated, again releasing H2SO4. So, that is how the amount of the acid released is high, and the system becomes far more acidic. And if you look at, if it acts upon a mineral like chalcopyrite over here, then it forms the soluble copper sulphide, copper sulphate. And similar reactions also could be written if it had been a zinc iron sulphide like sphalerite, or it would have been a lead sulphide. So, it dissolves the metal in the form of copper sulphate, and then so these are the reactions which take place above the water table, and below the water table the reactions that take place is that this copper ion, which is being transported through the fluid, is gets reduced to Cu2s, that is the chalcocite, or even CuS. So, these reactions are responsible, or these two sets of reactions, they operate on the above the water table and the below the water table, and explains the formation of the supergene sulphide enrichment. And here the it is just an example, or just the schematic presentation of the situation mineralogically. This is the primary or the hypogene ore, as we call them, chalcopyrite, pyrite, and it can have the silicates like albite, biotite, epidote, potash feldspar, and so on in this primary ore. and in the supergene blanket we can have bornite, chalcocite, covellite, pyrite, and some of the alteration mineral like alunite, which is a potassium aluminum sulfate mineral, and some clays and so on. And the least zone, which we labeled essentially as the iron hat or the gosan, but they have hematite, goethite, and sometimes even some gibbsite or kaolinite type of clay. So, the situation also can be explained, the mechanism, by the help of an EHPS diagram, where the appropriate reactions could be written. So, these are the stability field, as you could see. This is copper 2 plus, these are some of the silicates and the sulphate, brocanthite, antlite, chalcantharite, and this is the field of malachite, which is copper carbonate, hydrated copper carbonate. This is the one of the oxide forms of copper, that is tenorite. This is the other form of oxide of copper, cuprite, and as you could see here, the EH is increasing from cuprite to tenorite. And what is more important to observe here, that in such a situation we also do get native copper. There are many deposits, sulphide deposits, including the ones irrespective of their genetic affiliation, whatever sulphide body in the form that we presented as a cartoon in the previous figure. If the conditions are such, the appropriate pH and the EH conditions are such, we also can have formation of native copper as we see them, and the oxides, and they generally are within the oxidation zone, because we could see the pH stability of these oxide minerals like tenorite or native copper or cuprite generally will happen when the pH is much higher. So, the situation where the country rock is able to neutralize the acid that is generated by the process of pyrite oxidation, then the copper of the primary ore in these zones may not be able to be dissolved that efficiently. Some amount of copper will be left behind in the oxidation zone to form the minerals like tenorite and cuprite and some native copper as well. This is just to show you an example. This is a famous Malanjkhand copper mine in central India, details of which we will discuss when we will be taking up the Indian mineral deposits. Just to show as an example, this is the altered weathered granite at the top. This is the ore body which is exposed on the surface and is converted to a entire mass which is enriched with limonite, or this is exactly where the gosan which looks like. Just below the gosan, here we see that this is the ore, this is the zone which is the secondary enrichment zone, and the chalcocite and covellite ores minerals have a very typical black color, and they give such kind of an appearance, and sometimes these zones are also called as the sooty ore body in the mining geological terms. And if one goes further down, then the primary ore body is encountered. So, in such kind of an ore body, almost like for a vertical height of almost 20-30 meters and for 30-40 meters, such kind of zone generally is observed below the supergene oxidation zone, which is characterized by the presence of this gosan. So, these gosans actually, as we will be discussing sometime later when we take up exploration topics, they are very interesting. First of all, when such an ore body is undergoing supergene oxidation on the surface, and is a clear cut indication that there must be a secondary enrichment zone below, and more importantly the presence of an ore body in the subsurface, and that is what exactly we are looking for. So, these serve as very good indicators, geological indicators for exploration. That means the process of finding out new ore bodies or finding out ore bodies in areas where they are not known to be occurring. And these limonitic cap, which is the gosan zone, usually is there in the area where the ore body has a considerably fractured. That is how the fluid could percolate through the fracture zone, and they do display various types of forms which are known as the limonite boxwork, the gosans, which is basically the called as the boxwork in the mining geological term. Here are the 3 examples which are shown here. The first one is the typical boxwork which is produced from a chalcopyrite ore. These thick lines are the veins of quartz, because they are essentially the present in the quartz veins, in the mineralized quartz veins. So, these are the quartz veins, original quartz veins, in which the minerals, the primary sulphide minerals has been leached out and have been left behind by the interstitial limonite. So, this C, E and B are all the interstitial limonite, and has come from typical type of a copper deposit which are known as the porphyry copper deposit, which we will be discussing later on. And this pattern has come up from a quadrangular pattern where there is some cross structure and thin angular wave work. So, these are actually indications that what kind of an ore body could be expected below, whether it is a chalcopyrite rich ore body, or, and similarly we see that this is the kind of boxwork which is created if there is sphalerite rich ore body, because sphalerite by virtue of its morphology, its crystal habit and the way it forms in the fracture spaces in the deposit. After the sphalerite is leached out, the zinc is leached out by the acid that is generated on the surface, and these are again filled up by the limonite. This gives a look of a coarse cellular boxwork in sphalerite. This boxwork is a typical pattern which is coming out of galena rich ore, and here is a regular pattern. This is a diamond mesh type pattern. So, these processes which we have discussed, the surface operating processes, the mechanical concentration, the residual concentration, and this supergene sulphide enrichment, are essentially very efficient processes in giving rise to ore deposits, as well as getting the already existing deposit enriched to high grade values. So, they are even as important as the primary ore forming processes. Primary ore forming processes, when they form the ore body, what we have observed is the secondary or the surface operated ore processes have always upgraded or improved or further enriched the ore body, which essentially could be traced back to processes of the very enrichment process which we see fundamentally as ore forming process. So, we will be continuing our discussion through other deposit types. Thank you.